Welcome to the walkthrough for worksheet number 4. This is the worksheet that goes with our specific heat lab. So we've already seen the energy equations at the top, or two of them we have. The Q equals MC delta T, which we use when there's a temperature change in a system, and the Q equals MH, which we use when there's a phase change. Our new one that's related to the lab is this first one, that the energy gained by one thing in a closed system is equal to the negative energy lost by the second thing. And that's also related to our first question here. So the law of conservation of energy says that energy cannot be created or destroyed. So let's write that down. Can't be created or destroyed. And how that relates here is that the energy remains constant in a closed system. And in our lab, we were attempting to have a closed system. Sorry for the sloppy handwriting, it's hard to write on the screen. So we were attempting to have a closed system. And because of that, when we put the hot metal into the cold water, the metal heated up the water. That transfer of energy, the energy lost by the metal in our lab, all of it went into the water. None of it was lost because it was a closed system, which means the energy lost by the metal is equal to the energy gained by the water. And that is the logic we will be using for the calculations. Gained by the water. Now, in reality, our system was not perfectly closed, which means probably a little bit of energy was lost to the environment, but we attempted to keep it closed, and we are assuming it is closed for the purpose of the calculations. So let's move on to our calculations. Now, just to remind you how the lab worked, we had a piece of metal that we put into boiling water, and we let it come to equilibrium with the boiling water. And since boiling water is 100 degrees Celsius, that means the metal was 100 degrees Celsius to start. And then we quickly transferred it into our calorimeter, which was a styrofoam coffee cup. And there was room temperature water in the calorimeter. And we put the lid on, and we measured the temperature, and the hot metal transferred energy to the cool water until they eventually came to equilibrium. And then they both had the same final temperature because they came to equilibrium. So we are going to use that equation that we saw at the top, that the energy that was gained by the water is equal to the negative energy lost by the metal. And notice that if I added those two things together, I would get 0. So there's no net energy gain or loss in this system. If you prefer, you can actually do this as one equation, but I'm going to split it into 2 steps. Step 1 is I'm going to figure out how much energy was gained by the water. That can be measured because we know the temperature change of the water. And then I'm going to use my answer to step 1 to calculate not the energy loss, because that's equal to step 1, but use it to calculate the specific heat of the metal and then identify our metal. So that is going to be step 2. So for step 1, the energy gained by the water, because the water changed in temperature but did not change phase, we know that we are going to use our Q equals MCAT, MC delta T equation. The mass is going to be the mass of the water. Everything in this part is the water part. The specific heat will be the specific heat of the water. And the change in temperature is the change in temperature of the water, final minus initial. So if we look at our problem here, it says that it's put into 100 grams of water that is initially at 23.7 degrees Celsius. That would be our initial. And then the final is going to be the same final temperature for both the water and the metal, because they came to equilibrium. So now we can use the problem to fill in our numbers. So it says that We have our metal has a mass of 59.05 grams and it's heated to 100 degrees Celsius. And then it's put into 100 grams of water at 23.7 degrees Celsius. And they come to an equilibrium temperature of 27.8 degrees Celsius. So the mass of the water, it says 100 grams of water. So that's the mass of our water. The specific heat of water is a constant. It's written at the top of the page. This is liquid water. So it's 4.186 joules per gram per degree Celsius. The final temperature of both the water and the metal was 27.8 degrees Celsius. And the initial temperature of just the water, now remember, this is not the boiling water that we put the metal into. This is the cool water that's in our calorimeter. And so this is 23.7 degrees Celsius. And when we do the temperature change, and when we subtract 27.8 minus 23.7, that ends up being 4.1 degrees Celsius. So 100 times 4.186 times 4.1 degrees Celsius gives us the fact that the water absorbed 1,716.26 joules of energy. So that's how much energy was gained by the water. Notice I haven't rounded to sig figs yet. And that's going to be equal to the energy that was lost by the metal. So for the metal, it also changed in temperature. So we will also be using Q equals MCAT. And I'm going to change colors just to make it a little clearer. I will use red for the metal. So let's do this part in red. So our negative Q that's lost by the metal is going to equal the mass of the metal times the specific heat of the metal, which remember we don't know, that's what we'll be solving for, times the change in temperature of the metal. You have a couple options here. If you don't like to rearrange equations, you can just plug in all your numbers. I do prefer my equations rearranged, so I'm going to divide both sides by the mass of the metal and the temperature change so that I can get the equation to equal specific heat. So I will divide both these sides by M and the change in temperature so that I can solve just for the specific heat and have the equation rearranged. But that is not required if you don't like to rearrange. So the specific heat is equal to the negative Q over the mass of the metal times the change in temperature of the metal. And when we plug in our numbers, remember the negative Q is that thing we solved for in the first step of the problem, but negative this time. So negative 1716.26 joules. And the mass, remember it's the mass of the metal, so 59.05 grams. And then the final temperature of the metal is the same as the final temperature of the water. It's 27.8 degrees Celsius. The initial temperature, because it was in boiling water, is 100 degrees Celsius. So that change in temperature, when we subtract, ends up being negative 72.2 degrees Celsius. So negative 1,716.26 divided by 59.05 divided by negative 72.2. Sorry that I squished it in the corner here. But the answer, when you do the math, ends up being 0.40 joules per gram per degree Celsius. That's with 2 sig figs because our temperature change back with the water, the 4.1 degrees, had 2 sig figs. And although hopefully you can just, see the units for a specific heat up at the top of the page, it's always the same units. We can also get the units from our calculation. To calculate for the specific heat, we had joules on the top, divided by grams, divided by degrees Celsius, and that's what our units are. And remember, that means that it takes 0.40 joules of energy to heat 1 gram of this metal by 1 degree Celsius. So now that we have our specific heat of the metal, it says pure copper has a specific heat of 0.383. So is this sample copper? Now, the answer is maybe. It's probably not, though, because in general, assuming that we don't make any big mistakes in the lab, the only source of error that's hard to control is losing energy to the environment, which means usually our number is going to be a little bit lower than it should be. This is a little bit higher than the number that it should be. So it's more likely that our true answer, the true specific heat, is actually a little bit more than 0.4, which would mean that it's not copper. So because of heat loss to the environment, or we'll call it to the surroundings, because that's the word we often use in science, the true value is likely higher than our 0.4, which would mean not copper. But since we don't know specifically any errors, there are other errors like, errors in procedure you can make that would end up with an answer that's too high. Okay, so these two problems on the back are exceeds level problems. Exceeds level is solving for something else other than the specific heat of the metal. So this first one is, suppose a piece of pure iron with a mass of 21.5 grams at a temperature of 100 degrees Celsius is dropped into an insulated container of water. The mass of the water is 132 grams and its temperature before adding the iron is 20.5 degrees Celsius. What will be the final temperature of the system? So that's what we're solving for here, is final temperature, TF. We know the specific heat of the metal. It gives us here, it's 0.449 joules per gram per degree Celsius. So we're going to use our same equation, the Q gained. In this case, the Q gained, the energy gained is by the water, it heats up, is going to be equal the negative Q lost by the metal. Looks the same so far, right? Except for, instead of solving for the specific heat of the metal, we know that, we're solving for the TF, the final temperature. And something that's important to remember is because the system is at equilibrium, the TF for both the water and the metal is the same. So rather than splitting it into two steps, we need to do this as one big equation. And, it will involve a large amount of algebra. So both the energy gained by the water and the energy lost by the metal, both of those involve the Q equals mc delta T equation because both of them changed in temperature and not phase. So our sort of big version, when we expand it, we will have the mass of the water times the specific heat of the water times the change in temperature. And here I'm writing just TF, not TF of the water, because it's the same on both sides, minus the starting temperature of the water. And that's going to equal the mass of the metal times the specific heat of the metal times the change in temperature. Again, TF was the same on both sides because they're at equilibrium. So I'm just writing TF minus the starting temperature of the metal. So from here, it's plugging in the numbers and doing a lot of algebra. So we can look back at the problem and we see that the mass of the water is 132 grams. The specific heat of liquid water is on the equation sheet on the front. It's 4.186 joules per gram per degree Celsius. The final temperature is what we are trying to solve for, so we'll just write the variable. The starting temperature of the water, in this case, was given in the problem. It was 20.5 degrees Celsius. The mass of the metal, again, given in the problem. Oh, I just noticed I made a common mistake, and I'm glad I caught it, so hopefully you can catch it too. I forgot to write in my negative sign. I'm going to write it in red so that we don't forget. If you lose the negative sign, if I hadn't caught my mistake, I would end up with the wrong answer. It's a very common mistake. Even people doing walkthrough videos can make it. So it's negative because, remember, it is the energy lost. So the mass of the metal was given in the problem. It is 21.5 grams. And the specific heat of the metal is given in the problem as well. It is 0.449 joules per gram per degree Celsius. And the change in temperature of the metal is the final temperature minus the initial. And remember, the metal was put into boiling water, so its initial temperature was 100 degrees Celsius. So from here, we need to do some algebra. So first, we will multiply the two numbers in front of the parentheses. So 132 times 4.186. And I'm going to drop my units here just to make life easier. So that ends up being 552.55. Notice I'm not rounding to sig figs until the end. And then I will distribute that number across the parentheses. And I will do this on both sides. So 21.5 times 0.449 is negative 9.65. And that will be distributed across these parentheses. So when I do that, 552.55 times TF is just 552.55 TF. And then times negative 20.5 is minus 11,327. And that equals negative 9.65 times TF. Negative 9.65 times negative 100 becomes a positive because negative times negative is a positive. So it ends up being positive 965. Then I'm going to collect like terms. So 552.55 TF plus 9.65 TF on one side ends up being 562.2 TF. And then collect the other terms on the other side. So 965 plus 11,327 is 12,292. And then I divide both sides by 562.2. And I end up with a final temperature. For sig figs, this will be 3 sig figs. If you look back, we have 3 sig figs in the specific heat of the iron. We have 3 sig figs in our temperatures, and in the 21.5 grams, there's lots of 3 sig figs. So 3 sig figs in our answer. And so the answer will be 21.9 degrees Celsius. And it's always good to do a little logic check. Does this make sense? Is it between the starting and the ending temperature? And it is, because our water started at 20.5, our metal started at 100. It's between those two things. And remember, water has a very high specific heat, so it usually will not change a lot in temperature. All right, so our next question is very similar. So how much will the temperature of a cup of coffee at 95.7 degrees Celsius be reduced when a 45.1 gram silver spoon, gives you the specific heat of silver there, 2.33 joules per gram per degree Celsius at 21.9 degrees Celsius, is placed into the coffee and the two are allowed to come to thermal equilibrium? Assume that the coffee has the same specific heat as water, and this is a closed system. So very similar to before, we will start with the fact that the energy is gained by the spoon this time because it's the cold thing, and that's going to be equal to the energy lost by the coffee, the negative energy lost by the coffee. And just like before, the final temperature is going to be the same for both. So because both of them change temperature, they didn't change phase, we'll use Q equals MC delta T for both sides. And the M and the C and the delta T will be specific to that system. So the mass of the spoon times the specific heat of the spoon times the change in temperature. Remembering that since the final is the same for both, we will not be specific there. It's just the final temperature minus the initial temperature of the spoon. And that's equal to the negative, didn't forget my negative sign, mass of the coffee times the specific heat of the coffee times the change in temperature, final, same for both, minus initial of the coffee. And then we will plug in our numbers. The mass of the spoon was 45.1 grams. The specific heat of the spoon was silver. That was given in the problem. It is 0.233 joules per gram per degree Celsius. The final temperature is what we're trying to find. The initial temperature of the spoon was 21.9 degrees Celsius. And then don't lose the negative sign. The mass of the coffee is 183 grams. The specific heat of coffee we're saying is the same as water, so 4.186 joules per gram per degree Celsius. And then the final temperature, we don't know. The initial temperature of the coffee is 95.7 degrees Celsius. And so just like on the previous problem, we will multiply and then distribute. So 45.1 times 0.233 is 10.508. And I'm losing my units just for simplicity's sake. We will distribute that across the parentheses. 183 times 4.186 is negative 766.0. And that will also be distributed across the parentheses. So we end up with 10.508 times TF. And then minus, because 10.508 times negative 21.9 is 230.12. And that equals negative 766.0 TF. And then negative times negative is a positive. So negative 766 times negative 95.7 ends up with positive 73,309.8. We will collect like terms. So 10.508 plus 766 TF, you end up with 776.6 TF. And that equals collecting like terms on the other side, the 73,000 plus the 230, you get 73,540. Divide both sides by 776.6. And we end up with a final temperature with 3 sig figs of 94.7 degrees Celsius. But that's actually not the answer to the problem. The problem says how much will it decrease. So to find the change in temperature, you take the final minus initial, right? And the final temperature was 94.7 degrees Celsius. The initial temperature of the coffee was 95.7 degrees Celsius, which means our change in temperature is negative 1.0 degrees Celsius. It decreased by exactly 1 degree Celsius. So always make sure you read the problem and that you're answering the question that the problem asks.